So we'll proceed to a new topic today. The topic is on mass transfer of drops and bubbles. This topic will be separated into three sections or three parts. So let's start with the first part. Number 5, heat and mass transfer of a spherical particle in a flow field, okay, including the numerical approach to mass transfer of spherical particle in a laminar flow, and then reach Marshall correlation and comparison with numerical data. Lastly, mass transfer coefficient for spherical or single sphere. A single sphere. Okay, so introduction. So we look at dimensionless groups. All right. So basically, what we are using for mass transfer actually derived from heat transfer. So what you have learned in heat transfer actually applicable to mass transfer. Okay. Now the flow condition for both heat and mass transfer actually, and the geometry must be the same. Okay, then we can interchange use the same thing in mass transfer for mass transfer. In heat transfer data, you can also use in mass transfer. Okay, now if you look at the table, okay, so Reynolds number is applicable to both heat and mass transfer. Smith number is used in mass transfer instead of Planck number. Sherwood number, Nusselt number. Okay, so these are the different Grashof number for heat transfer and mass transfer. The definition, the equation is slightly different. All right. So next we look at the palette number. Okay, between mass transfer and heat transfer. Okay, there are some differences in the equation. Actually, we are correlating to diffusion coefficient or the heat transfer diffusivity. Okay, Stanton, okay, number, or what you call it, Clinton and Coburn, J factor. Okay. Yeah, some different. Only I think the difference is the Smith number and Planck number lah. Or not. Okay. Okay. So use of analog would then produce mass transfer coefficient corresponding to no net mass transfer. In turn, corresponding most closely to Kg prime, Kc prime, or Ky prime. Okay. Sherwood number are commonly written in the term of any of the coefficient, but derived by replacement of Nusselt number for the use when the net mass transfer is not zero. They must be taken as a Smith number. Okay, so F is used for the following equation. Okay, section 2 is on creeping flow around spherical particle. The motion of spherical particles in fluid medium is of fundamental concern in various industry and environmental problem. Okay, because in industry we do apply a lot of spraying mechanism, okay, to produce fine droplets for many purposes lah. For example, to dry or to paint, even in the car industry, automobile industry, car industry. Okay, we spray the paint on the car body, right? For environmental problem, for example, aeration is needed for the water treatment plant, so we are introducing air bubbles. So all these processes require the understanding of the mass transfer of these fine droplets or fine particles. All right, so figure 10.1 shows the flow around a spherical particle when it's placed in a very slow and uniform flow. Okay, a slow and uniform flow. Okay, so actually what we are going to discuss here is the model, the equation to describe the streamline around spherical particle. So we are only look at the ideal cases. Okay, when you have turbulent flow, when the flow is fast, we have a continuous or viscous flow, the pattern of the line is different. Okay, and it's very complicated. All right, so we can actually cannot solve. We cannot solve the problem using simple manual calculation, or even with our MATLAB we cannot solve this. We need more complicated software. Okay, so CFD maybe continuous computational fluid dynamics software to solve that, because it involves a lot of equations to create the streamline and the interaction between the streamlines. Okay, now we have to assume there is no separation of flow from the surface of the particle. Okay, well, this type of flow is called creeping flow, very uniform, very slow flow, very nice flow. Okay, the inertial term in the equation of the motion is negligibly small comparison with the viscous term, and hence can be neglected. Okay, so we can neglect the inertial term because the particle is flowing in a very calm flow. All right, let's look at figure 10.1. This is the illustration of a sphere particle inside creeping flow, the streamlines. Okay, so the line can actually described by equation 10.1. This is the equation. You can see sinusoidal pattern right around the spherical particle. Okay, so this equation is actually known as Stokes flow. All right, because it's derived by Stokes in 1851. Okay, so Stokes had already come up with the analytical solution, so it's solved by mathematically. Okay, so he gave us this equation 10.1. Okay, Stokes flow equation. Okay, the equation of motion of spherical particle in creeping flow in terms of streamline in spherical coordinate. Okay, we use this equation 10.1. Okay, even though you want to solve this using a manual calculation, is already a challenge. All right. Okay, so the boundary condition of the equation 10.1. So we base on the distance, the distance from the center of the spherical particle. Okay, so the big R is really the radius of the spherical particle. Is actually equivalent to diameter of the particle divided by 2. Okay, so we can use 10.2 when you are looking at the velocity in terms of the radius. Okay, the distance from the center of the droplet, or based on the angle, the radian. Okay, using the radian also you can use 10.3. All right, when the distance is very far from the center of the spherical particle, the r equivalent to infinity, so we can actually approximate the velocity equals to u times cosine in angle of the streamline. All right. Okay, if the following equation 10.5, the stream function is assumed, which will automatically satisfy the boundary condition at far point far from the particle. So this is the equation 10.5 when it's the streamline is very far from the spherical droplet. Okay, so analytical solution of 10.1 can easily be obtained by methods of separation of variable. Okay, so what we can get for creeping flow, we can use 10.6, the streamline equivalent to this simplified function. So using this one, uh, we can actually solve it with simple mathematics. Okay, compared to 10.1. All right. Okay, now if you substitute 10.6, equation 10.6 to 10.1 and 10.2 and 10.3, okay, in terms of radial and tangential component, okay, so you get 10.7 and 10.8, the velocity. Yeah, okay, so the shear stress due to the friction of the surface of the particle at the angle theta is given by 10.9. Okay. Okay, and then we can have also frictional drag acting on the surface of the particle. Okay, so 10.10 is the equation to look at the frictional drag. All right, and then the pressure distribution on the surface of the particle. Okay, because the streamline is acting at spherical surface, so the pressure on the spherical particle is different. Okay, so 10.11 is the equation to describe the pressure distribution. Equation 10.12. Okay, the drag or pressure drag. The drag due to the axial component of the pressure on the surface of the particle, okay, can be calculated by integrating the axial component of the stress on the surface of the particle with a small surface element following the following equation lah. Okay, the drag force 10.13. Okay, sum of the frictional drag and also form drag. Form is actually the pressure drag. So altogether, summation of total drag force is equivalent to 10.13. 10.13 is referred to Stokes law of resistance, and when it's applicable to the flow around particle, it's called Stokes flow. Okay, the drag coefficient. Okay, drag coefficient is very important. So equation 10.14. Okay, but at a certain Reynolds number, we can even simplify the 10.14. For example, if the Reynolds numbers within the Stokes law condition, we can use drag coefficient equals to 24 over Reynolds number. This general equation is applicable in certain situation. Okay, we cannot use the same one, this equation for all the condition. Okay, Reynolds number for particle equivalent to density times diameter times the velocity over viscosity. This is very important. Reynolds number pro VD or pro UD over mu. Mu is the viscosity. Alright. Now this is important. The equation 10.15, the drag force, is only applicable when the creeping flow is meet the requirement of this, the low Reynolds number less than 0.1. Reynolds number must be less than 0.1. Only you can use equation 10.15 to calculate the drag coefficient.